Imagine the universe vast and infinite. Now imagine a theory that could explain the invisible force that governs it all, gravity. Enter Albert Einstein, a physicist who didn't just imagine but revolutionized our understanding of this force with his groundbreaking theory of gravity, also known as General Relativity. In the early 20th century, Einstein presented a new perspective on gravity, one that moved beyond Isaac Newton's classical ideas. Where Newton saw gravity as a force pulling apples from trees and moons around planets, Einstein envisioned it as something far more intriguing. He saw gravity as a curvature in the fabric of space-time itself, caused by massive objects like stars and planets. This was a radical departure from the norm, a revolution that transformed our comprehension of the universe around us. Our journey into the deep realms of this revolutionary theory is just beginning. So buckle up as we embark on a journey to decode Einstein's revolutionary theory of gravity. At the heart of Einstein's theory lies a simple yet powerful idea, the principle of equivalence. This principle plays a pivotal role in our understanding of gravity. It asserts a profound truth. There's no discernible difference between the effects of gravity and those of acceleration. Picture yourself in a sealed, accelerating spaceship. Without any windows or means to observe the outside world, you'd feel a force pulling you back. But is this force due to the ship's acceleration, or is it gravity? According to the principle of equivalence, there's no way to tell. This concept led Einstein to a radical conclusion that upended centuries of scientific thought. He proposed that gravity isn't a force transmitted across space, an idea deeply rooted in Newtonian physics. Instead, Einstein saw gravity as a result of the way mass distorts the fabric of space-time. Thus, gravity, according to Einstein, is a curvature of space-time caused by mass. Picture space-time as a fabric. Now, what happens when you place a massive object on it? Well, imagine you're spreading out a perfectly flat sheet, and then you place a bowling ball in the middle. The sheet dips around the weight of the ball, creating a curve. This is the concept we're exploring, but instead of a sheet, we're looking at the fabric of space-time, and instead of a bowling ball, we're considering celestial bodies like planets and stars. In Einstein's theory of gravity, or general relativity, space-time isn't a passive stage where the drama of the universe unfolds. Instead, it's an active player, distorted and shaped by the mass and energy within it. This distortion is not just a theoretical concept, but the very essence of gravity itself. When a massive object like the Earth or the Sun resides within space-time, it causes the fabric of space-time to curve around it, much like our bowling ball distorting the flat sheet. But what about smaller objects like satellites or other celestial bodies? When these smaller entities move through this curved space-time, they don't move in straight lines. Instead, they follow a curved path, a trajectory that's influenced by the curvature caused by the massive object. This curvature, this distortion in the fabric of space-time, is what we perceive as the force of gravity. It's not that the Earth is pulling an apple downwards. It's that the Earth has curved the space-time around it, such that the apple's natural path is to move towards the Earth. The beautiful simplicity of this concept is that it applies universally, from the motion of planets around the Sun to the path of light passing near a star. It's not an invisible force that determines the path, but the very structure of space-time itself, shaped by the mass and energy within it. So the path of a satellite or a planet isn't determined by an invisible force, but by the curvature of space-time itself. Einstein's theory isn't just beautiful, it's mathematically rigorous. Einstein's general relativity is more than just a concept. It is a set of equations that express the intricate relationship between mass, energy, and the curvature of space-time. The crux of these equations is a mathematical object known as the metric tensor. This tensor is a way of encoding all the information about the curvature of space-time in a given region. It's a bit like a map, telling us how space-time bends and twists in response to the presence of mass and energy. But how does it do that exactly? The equations of general relativity relate the distribution of matter and energy in the universe to the curvature of space-time. In other words, they tell us how the presence of mass and energy warps space-time, and in turn, how this warped space-time influences the motion of objects. This is no easy task. The equations of general relativity are notoriously difficult to solve, requiring advanced mathematical techniques. Yet they've proven their worth time and again, allowing us to make predictions about phenomena such as black holes, gravitational lensing, and the expansion of the universe, to name just a few. These equations, though complex, provide a comprehensive framework for understanding gravity on both large and small scales. So, while the mathematics of general relativity might seem daunting, it's the key to unlocking the mysteries of the universe as we know it. Time, as it turns out, is also a puppet of gravity. This may sound like a line from a science fiction novel, but it's a reality in Einstein's universe. One of the intriguing effects of general relativity is a phenomenon known as gravitational time dilation. This principle suggests that time doesn't tick at the same rate everywhere in the universe. Instead, it slows down in regions where gravity is stronger. Think of it this way. If you were near a massive object, such as a black hole, your watch would tick slower than it would if you were floating in the emptiness of space far from any celestial bodies. This isn't because your watch is malfunctioning, but rather due to the warping of space-time caused by the black hole's enormous mass. As a result, time itself trudges along at a slower pace the closer you are to such a massive object. This isn't just theoretical musings either. Gravitational time dilation has been experimentally verified. One such example is the Pound-Rebka experiment, where gamma rays were observed to experience a gravitational redshift when climbing out of a gravitational well, essentially proving that time runs slower in stronger gravitational fields. So, in the grand cosmic ballet, not only does gravity choreograph the movements of stars and galaxies, it also sets the tempo for the march of time itself. This fascinating consequence of general relativity has been experimentally verified, further solidifying Einstein's theory. Einstein's theory didn't just redefine gravity, it also predicted the existence of gravitational waves. Now, what are these waves, you ask? Imagine throwing a stone into a pond. The stone's impact sends ripples across the water, right? Gravitational waves are similar, but instead they are ripples in the fabric of space-time caused by the acceleration of massive objects. But how do we detect these waves? Enter LIGO, the Laser Interferometer Gravitational Wave Observatory. In 2015, LIGO made the groundbreaking detection of gravitational waves resulting from the collision of two black holes. This was a monumental event, not only because it confirmed the existence of these elusive waves, but because it validated Einstein's general relativity in a new and profound way. The discovery of gravitational waves opened a new era in astrophysics, confirming a key aspect of general relativity. So next time you gaze at the stars, remember there's a whole lot of rippling going on out there. Einstein's general relativity has stood the test of time. From the principle of equivalence to the curvature of spacetime, the theory has given us a profound understanding of the unseen forces that govern our universe. It's a mathematical marvel, a symphony of equations that interweave matter, energy, space, and time. It has opened our eyes to the concept of gravitational time dilation, where the strength of gravity can influence the passage of time. It has predicted the existence of gravitational waves, ripples in space-time that were only confirmed in the second decade of the 21st century. Einstein's theory of gravity is no longer just a theory. It's a proven, tested and retested cornerstone of modern physics, a key that unlocks the secrets of the cosmos.